A spirometer is an instrument used mainly by athletes to measure air capacity of the lungs. The higher your spirometer reading, the more gases your lungs can take in inspiration, breathing in. It shows the different lung volumes and capacity for people. Some of the things it shows is total lung capacity, which is the total volume of air the lungs can hold. Shows tidal volume, the amount of air breathed per breath. For tidal volume, this is where the record is. Residual volume, the air that can't be breathed out. This is protected for the lungs because it stops them deflating. It also measures vital capacity, the maximum air you can breathe in and out. So if the tidal volume increases and we breathe more air in, then that means that we'll use our IRV, inspiratory reserve volume, expiratory reserve volume, which at rest are 3,100 milliliters and around 1,000 milliliters. The IRV and ERV are large reserves available if needed. For example, if tidal volume increases because you're exercising, you need to breathe in and out more, which means that the record goes up more towards IRV and ERV, and they are used a lot more. They are like an overdraft in a bank, because if you run out of air, you use your IRV to breathe more in, whereas you use the ERV to breathe more out. Our total lung capacity is measured by adding our IRV, ERV and RV residual volume. At rest it's 6,000 milliliters. The residual volume is the air remaining after the ERV, expiratory reserve volume, is exhaled. At rest this is 1 litre, whereas during exercise it's also 1 litre. Vital capacity is IRV plus ERV minus max exhalation after max inhalation, so after max air is breathed in. At rest and exercise this is 5 litres. The inspiratory reserve volume, or IRV, is the air that could be exhaled, so at rest it's 3 litres. That exercise it's less because it's used during exercise, because you have to breathe in more and deeper, and the ERV is the air that could be exhaled, deeper breath out. So at rest it's 1 litre, whereas exercise it's also less, because when you need to use it as a backup air volume when you breathe in, when you breathe out. These are my test results for heart rate from the lactate threshold test. So on the left it shows my blood lactate profile, with power measured in watts on the x-axis and heart rate measured in beats per minute on the y-axis. The more power is increased, so 21 watts each stage, the more heart rate increases. And on the right it shows my heart rate maximum and minimum reserves during the VO2 max during the lactate threshold test. As you can see, the red line, which is showing heart rate minimum reserve, goes under 0 to minus 0.7, whereas the blue one only goes down to 0, where they both plateau. However, they are where they start to decrease is around a similar point, 0.7, 0.8. Cardiac output and stroke volume graphs. So the left one is my stroke volume graph. As you can see, the blue line is showing the amount of stages, whereas the red line is showing my stroke volume values. The x-axis is showing the number of stages, whereas the y-axis is showing the value. You work out stroke volume by doing ESV, end systolic volume, minus end diastolic volume, and stroke volume is measured in milliliters. stroke volume goes up as the stages are increased because the power was increased each stage during the lactate threshold test, which means we need more volume of blood pumped from the left ventricle per beat to get round the body. However, it plateaus at stage 5 through to stage 6 because our during diastole and systole our heart is trying to fill up, but it can't fill up anymore because it's pumping too fast, which means blood can't get into it, so therefore stroke volume decreases or plateaus. The right image is showing cardiac output. As power goes up, cardiac output, which is measured in litres per minute, goes up because that means that we need more volume of blood ejected by the ventricles per minute to get around the body and to the muscles. Q equals HR plus SV. This means cardiac output equals heart rate plus stroke volume. If you increase heart rate, then cardiac output and stroke volume will increase, whereas if you increase stroke volume, heart rate and cardiac output will also increase. Q is cardiac output. This is the amount of blood pumped by the heart per minute. HR is heart rate, the amount of times your heart beats per minute. Stroke volume is the amount of blood pumped from the left ventricle per minute. Heart rate is measured in beats per minute. Stroke volume is measured in milliliters, and cardiac output is measured in liters per minute. At rest, cardiac output is 5 liters per minute. During exercise, it's 13 liters per minute. In the anticipatory rise, which is where just before you start, the nerves, excitement cause your heart rate to rise, and your cardiac output and stroke volume, it's 8 liters per minute. During submaximal exercise, it's 10 liters per minute. During maximal exercise, it's 20 to 30 liters per minute. For heart rate at rest, it's 70 beats per minute. During the anticipatory rise, it's 100 beats per minute, and during exercise, it's 170 beats per minute. The submaximal is 100 to 130 beats per minute, and the maximal is 220 minus age. Stroke volume at rest is 70 milliliters. Anticipatory rise is 90 milliliters, and during exercise it's 110 milliliters. The submaximal is 80 to 100 milliliters, and the maximal is 100 to 120 milliliters. Different intensities. During maximal exercise, in the graph, it slowly and gradually increases until it slowly decreases at the end, rather than plateauing like submaximal does. During submaximal, you have 4 stages where it goes so pre-exercise, anticipatory rise, rapid increase, it then plateaus before a rapid decrease at the end during the recovery stage, whereas there are 3 stages during maximal exercise: anticipatory rise, rapid increase, and recovery or rapid decrease. ANS control of heart rate, or SAM. So this is where chemoreceptors, baroreceptors, proprioceptors, and thermoreceptors send feedback to the medulla oblongata. The chemoreceptors send feedback about chemical changes in blood. Proprioceptors detect muscle tension and send feedback about the muscle tension, whereas baroreceptors monitor pressure changes and send feedback about that. The thermoreceptors measure temperature and send feedback to the medulla oblongata. The medulla oblongata then sends an impulse through to the brain to the SA node, telling it to either increase or decrease heart rate depending on the feedback from the 4 receptors. The sympathetic nervous system will increase heart rate because it releases hormones catecholamines, epinephrine, and norepinephrine to accelerate the heart rate along the accelerator nerve, which speeds up heart rate, whereas the parasympathetic nervous system, PNS, releases acetylcholine, which slows down heart rate. and the vagus nerve decreases heart rate. Blood pressure. Blood pressure is the pressure of blood against the artery walls. It is measured in millimeters of mercury and it is typically 120 over 180. The top number, 120, is systolic pressure, whereas the bottom number is diastolic pressure. The blood pressure resistance is to do with the peripheral resistance, which is where there's blood viscosity, blood length of vessels, and diameter effect resistance. By the blood vessel diameter, the smaller the diameter, the more pressure, whereas the larger diameter, less pressure because blood can flow more easily through it. Blood viscosity is how easily the fluid particles can slide past each other, or how thick the blood vessels are. So the higher the viscosity, the slower the blood flow, because the fluids can slide less easily past each other, so there's more pressure building up. Whereas the lower the viscosity, the faster the blood flow, so the lower the blood pressure. The longer the vessel, the more resistance equals the more higher blood pressure, whereas the smaller the vessel, the lower the resistance, the lower the blood pressure. Here on the right you could see at normal it's 80 to 120 over 60 to 80. Whereas if you get to this stage, where your blood pressure is over 180 over more than 110, you should see a doctor. The blood pressure equation. So BP equals Q times resistance to flow. Resistance to flow depends on whether the blood vessel constricts or dilates, and also if it's blocked by fats, it affects resistance. If resistance increases, cardiac output and blood pressure also increase, and the same if cardiac output increases, so does resistance and blood pressure. Blood pressure in different vessels. So me and Parsa did 4 exercises, isometric, maximal, submaximal and isotonic, and after each of them we measured our blood pressure using a sphygmomanometer, which we connected up to our arm to measure our blood pressure. For rest we measured it. Mine was 110 millimeters of mercury over 38. Isometric we did the plank, and mine was 112 over 82 millimeters of mercury. We did at maximal exercise, we did 1 minute high knees, and my blood pressure was 147 millimeters of mercury over 106. We also did submaximal exercise, 20-second jog on the spot. My blood pressure was 132 millimeters of mercury over 106. And finally we did isotonic exercise, which we did 30 squats, which my blood pressure was 124 millimeters of mercury over 94. And these are shown in this graph here. So the bottom one is diastole values and the top one is systole. And there you go, are our values.